Hello and welcome back to California Geology. I am Dr. Robert Lopez. Today I want to talk about the Death Valley region and the highly extended terrains that occur there. Recall that I mentioned earlier that Death Valley has experienced 100% extension, so an enormous amount of extension. And some of that is manifested in these strange features called turtlebacks. And the turtlebacks are kind of dome-shaped, turtleback shaped. They all seem to be plunging toward the northwest, sort of tilted. And then what's more, not only are they seem to be sheared or extended, but they also seem to have some sort of compression because they're shaped like domes, plunging domes or anticlinal forms. So they're really quite strange. And so there's a variety of scenarios to try to interpret the history of how the kinematics or the structural history occurred to make these strange features. So if we go back to our slide here, remember Death Valley is known as a half graben because there's a detachment fault or a normal fault only on one side. And so it's going to be a special type of normal fault is where it's steeper near the surface, but as you go deeper down, it's going to be a shallower angle. So as the angle gets less steep, we call these detachment faults, right? And they accommodate quite a bit of extension. So what could it account for in Death Valley? One interesting thing that's also happening here is at some point these detachment faults will go down to a depth of 8 kilometers, 10 kilometers. And at that point, you're getting to temperatures where the rock will deform, but it won't be brittle. It won't break. So up here, the rock may break as it's deformed. So we call this brittle deformation in this upper plate. But the lower plate down here, below the detachment fault, will deform in this fashion called ductile deformation. And ductile deformation refers to flowing like plastic, getting smeared. In fact, the type of rock that forms here is a rock called myelinite. And myelinite is a smeared rock, myelinite. So, and it occurs around fault zones, right? And what's more, these myelinite rocks are going to be old because they're deeply buried. And now as we extend this terrain, as we move these upper plate rocks away, slide them away, we're going to expose these deeper rocks up to the surface. So these myelinite rocks will be exposed here so we can observe them. Now, so that's what's going to happen here. And also there's some other secondary faults that kind of join in with the detachment surface here. And these faults are said to be listric. So these are listric. So these are minor faults, really part of the same detachment system, but these listric faults will join up at depth with this main detachment. Now, let me say a couple more words about the turtlebacks, and I'll go to the PowerPoint. So these turtlebacks are highly extended old basement rocks brought to the surface. So remember, they've been smeared. They have that myelinite imprint, right? And in the Black Mountains, that's where we're going to see these, right? So if we go back to the top here, they're going to occur in these Black Mountains in Death Valley. So in the Black Mountains, we find that there are 3 of these turtlebacks. The Badwater turtleback, Copper Canyon turtleback, and one to the south called Mormon Point. Also, in the Death Valley region, a little bit to the northeast, there's this place called the Amargosa Chaos, because when geologists first looked at it, it's riddled by faults and folds, but it also seems to be another one of these turtleback structures where the Paleozoic cover has been removed, stripped away, right? And so what you're showing, you're bringing up this Precambrian basement and exposing it to the surface. So there's a couple of regions where we see these turtleback structures. So at the Black Mountains, and over here at the Amargosa Chaos. A couple more things to say about turtlebacks. So again, they're large structural features. They're going to be elongate. They're going to have this plunging dome type structure, almost like an anticlinal, an upward arching fold type structure. And again, they're composed of Precambrian rocks. So remember, they're going to be older than about 542 million years old. So remember, the Cambrian is the first period of the Phanerozoic eon. So we're looking at older basement rocks, no fossils down here. And they look like upwardly convex folds, so these anticlinal structures, right? And again, the rocks are smeared, and usually the surface is this carbonate rock, like a limestone, some sort of limestone it's easy to deform, right? It's a weaker rock. And then beneath the limestone will be these foliated metamorphic gneisses. So I got this from an article by Troxel and others who have worked in this Death Valley region since really the 1960s and kind of figured out what's been going on here. So I made some sketches from their models. And here we're looking at just before extension begins, where we're starting to break up the surface rocks. So these will probably be the Paleozoic rocks, and then as you go, maybe Mesozoic, Cenozoic, and younger cover rocks at the top. And then we'll see the carbonates are this kind of darker pink area I've outlined here, and this would be the metamorphic gneiss down in here, right? These metamorphic gneisses that are going to be in the middle. Now, as you have extension, you're going to pull this apart here. As we pull that apart, we'll find that these blocks are kind of like books on your bookshelf. They start leaning. As the books on the bookshelf start leaning, you'll get these little ridges that form there, right? And then those little ridges, eventually the blocks start sliding down. And so in the second picture down here, I'm showing the blocks have slid down some considerable distance, right? So they're kind of slumping down. And while that's happening, this metamorphic core complex, or this folded gneiss, and the overlying carbonate rocks, the myelinite, get moved to the surface to expose this turtleback structure, right? So you're bringing up that lower plate myelinite rock to the surface, again in this highly extended terrain. And here I kind of tried to draw a block model here, showing this is the kind of a little block where these are faults, right? So they'd be the various faults we see here, and the blocks are slipping down here, slumping off, and you're exposing these dome shape. And they're kind of plunging toward the northwest here, right? Plunging toward the northwest. And so another thing that's important here, besides just that you're bringing up these old rocks, because the rocks are here. In fact, these myelinite rocks are about 1.7 billion years old. Remember, GA stands for billions of years. But what's interesting is the Paleozoic rocks, the ones that I'm showing over here in this little cartoon, they're probably there. In fact, there's some exposures still there, little bits that the Paleozoic rock they're still there. So that's evidence that the rocks have been there in the past, that they've been stripped away. So in fact, geologists estimate that there's been about 20 to 30,000 feet of this Paleozoic or late Precambrian rocks that are missing. These are sedimentary rocks that should be above these, but they're missing. And part of the evidence is that there is an intrusive here. In fact, this is a late Cenozoic intrusive. In fact, I think they're primarily diorites. So it's a plutonic rock. They're young, anywhere from 14 to about 6 million years old. So they're relatively young intrusives. And these intrusives have a chemistry and in fact, we call them geobarometers. We use a barometer to measure pressure. So the geobarometer, which is a certain mineral, the geobarometer in these rocks indicate that these rocks formed at depth, at least 20,000 feet deep. So if we write the word here, we're going to have a geobarometer. So it measures pressure, this geobarometer. And it's primarily the hornblende crystals. We can use the iron and magnesium ratios to look at proxy to pressure. So if these are forming at 20,000 feet deep, that means that there must have been at least 20,000 feet of rock above them. And so based on other places where the Paleozoic rocks are exposed in the Death Valley region, there's up to 30,000 feet. So that's anywhere between 20 and 30,000 feet are missing. And so where do those rocks go? Some geologists speculate that those rocks have been moved over to the Panamint Range, because the Panamint Range has quite a bit of thickness. Remember, the Panamint Range is to the west of the Black Mountains here. And so that's about 80 kilometers away. So these Neoproterozoic, late Proterozoic, and Paleozoic rocks have been stripped away by this detachment faulting, and now they're 80 kilometers away over in the Panamint Range.